We now take up inflection points, and here we have to keep this in mind that more often than not, functions that we study in economics are convex in some parts of the domain and concave in other parts of the domain. So the points at which the function changes from being convex to being concave, or the points at which the function changes from being concave to being convex, those points are called inflection points. So if I'm asked to define inflection points in a general sense, I can say that these inflection points are the points at which a function changes from being convex to being concave, or vice versa. These are inflection points. Now, if I want to understand clearly what these points are, I can say that, let's say I have a twice differentiable function f, twice differentiable function f. We have this function, and when I say that point C in this case is an inflection point, in this case point C is an inflection point if there is an interval A to B, open interval, containing C, containing little c, such that either of the following two conditions holds. So we have a twice differentiable function f. We have a twice differentiable function f, and here point C is an inflection point if you have an interval a to b. It's an open interval that contains c, such that either of the following two conditions holds. The first condition is f double prime x is greater than equal to 0 if a is less than x less than c, and f double prime x is less than equal to 0 if c is less than x less than b. Either this holds or this, wherein now we just reverse things. F double prime x is less than equal to 0 if a is less than x less than c, and f double prime x is greater than equal to 0 if c is less than x less than b. So the point to note here is, in this case, obviously x is equal to c would be the inflection point. So basically what we are trying to say is that when I say x is equal to c is an inflection point, that just means f double prime x, it changes sign at c. So to the left of c, if it is greater than equal to 0, to the right of C if it is less than equal to 0. So clearly it is changing sign at C. So in this case, the function here the function changes from being convex to concave. Convex to concave. And here the function changes from being concave to convex. Basically, if f double prime x, if it changes sign at C, that just means x is equal to C is an inflection point. Now, if we look at the graph, and then we can say that C, f of C, this represents inflection point on the graph. And in fact, when we talk about x is equal to C, x is equal to C is the inflection point for the function. X is equal to C, that is the inflection point for the function. The point that I'm trying to make here is, at x is equal to C, f double prime x changes sign. And that just means x is equal to C is our inflection point for the function, that means. Also, if we look at the graph, we take up x is equal to C, and then you locate f of C. So C f of C, that would be the inflection point on the graph. X is equal to C is an inflection point for the function. And just to understand this, we can take the help of a diagram. Here in figure 9.21, we see that point P is an inflection point on the graph. Okay, so this point is C, f of C. This is the inflection point on the graph. X is equal to C is the inflection point for the function. That's the little difference here. Inflection point on the graph is C, f of C. Inflection point for the function is the point at which the function changes from being convex to concave, or vice versa. So x is equal to C is the inflection point for the function. And in this case, we see that the function changes from being convex to concave. So here it is convex and here it is concave. In fact, if you look at figure 9.22, this actually shows the profile of a ski jump. So the figure 9.22, it actually shows the profile of a ski jump. And in fact, we see that if we look at point P is the inflection point on the graph. And here we see that the hill is steepest. And in fact, here, when I say point P is the inflection point on the graph, if we just think of it as a graph, it is the inflection point. Point P is the inflection point. I can see that the function here changes from being concave to being convex. So it changes from being concave to being convex. This is the profile of a ski jump. Point P is the inflection point, and here we in fact see that the hill is steepest. Now let's take a look at test for inflection points. So that's a very important point to note. Test for inflection points. Again, let's say we have a function f. F is a function with a continuous second derivative in an interval I, and suppose here, and let's again say that in an interval I, then we can write that C is an interior point of I. So we are now considering a test for inflection points, and here we have f as a function, and this is a function with continuous second derivative in an interval I. Also, C is an interior point of I. Now we consider two cases, two very important points. If C is an inflection point, then f double prime C is equal to 0. Now that just means that f double prime C is a necessary condition for C to be an inflection point. Please get this right, that it is not a sufficient condition. And when I say if C is an inflection point for f, let's say this is the case, point for f, then this is the case. If I want to prove this, how do I go about it? I start with C being an inflection point for f, and then I move towards f double prime C being equal to 0. So if I know that C is an inflection point for f, that just means that if that's the case, it just means that f double prime x changes sign at C. That means this: if C is an inflection point for f, that just means f double prime x, it changes sign at C. What does that mean? That means we can say that okay, so I know that C is an inflection point. That just means this: f double prime x less than equal to C, sorry, it's less than equal to 0. As I said, it changes sign at C, so it is less than equal to 0 on one side of C, and f double prime x is greater than equal to 0 on the other side of C. And that just means that this just implies that f double prime C is equal to 0. We see here that on one side of C, f double prime x is less than equal to 0. On the other side of C, it is greater than equal to 0. What does that mean? That means at C, it is equal to 0. So f double prime C is equal to 0 in that case. That's one point to note. And the second point to note is this: if f double prime C is equal to 0 and f double prime changes sign at C, then C is an inflection point for f. Again, here we are going to consider the case that f double prime, it changes sign at C. It changes sign about point C. That just implies, according to the definition we have written earlier, that C is going to be an inflection point for f. As simple as that. It's actually reiterating what we know from before, that f double prime changes sign at C, and this implies C is an inflection point for f. Also, if we again get back to this point, let's get back to the fact that if C is an inflection point for f, then f double prime C is equal to 0. We have to be careful here that again f double prime C is equal to 0, that the second derivative at that point is 0. That's a necessary condition for that point to be an inflection point. It is not a sufficient condition. When I say f double prime C is equal to 0, that does not imply in itself that f double prime changes sign at x is equal to C. So that's very important to understand. When I say that C is an inflection point, that means f double prime x is going to change sign at C. The fact that f double prime C is equal to 0, that does not imply that f double prime changes sign at x is equal to C. So f double prime C is equal to 0, it's a necessary condition for C to be an inflection point. However, it is not a sufficient condition for C to be an inflection point. So given all this, let's take up a question, and in fact that will help us clear this point, that f double prime C is equal to 0, it's a necessary but not a sufficient condition for C to be an inflection point for f. So we take up this question. Show that f of x is equal to x raised to the power 4. This does not have an inflection point at x is equal to 0, even though f double prime 0 is equal to 0. So here, to go about this question, what we have to do is, first let's write f of x is equal to x raised to the power 4. And now let's think of f double prime x, which I know is 4x cubed, and then I take up f. So first we take up f prime x, which I know is 4x cubed. Then I take up f double prime x, which I know is 12x squared. So I can see here that f double prime 0 is definitely equal to 0. And we have to be very careful that for all x not equal to 0, f double prime x is in fact greater than 0. So what we see here is that if x is not equal to 0 in this case, f double prime x is greater than 0. So f double prime x is greater than 0 for all x not equal to 0. That means to the left of 0, f double prime is greater than 0. To the right of 0, also f double prime is greater than 0. Because I know that f double prime x is greater than 0 for all x not equal to 0. What does that mean? To the left of 0, to the left of x is equal to 0, f double prime is greater than 0. To the right of x is equal to 0, f double prime is greater than 0. That just means that f double prime is not changing sign at x is equal to 0. And that's a very important point to understand, that it is not changing sign at x is equal to 0. And if it is not changing sign at x is equal to 0, that just means x is equal to 0 is surely not an inflection point. Even though I know that f double prime 0 is 0, but x is equal to 0 is not an inflection point precisely because f double prime does not change sign at x is equal to 0. So if f double prime x is greater than 0 for all x not equal to 0, that means I can say f double prime does not change sign at x is equal to 0. And this just implies that x is equal to 0 is not an inflection point. Had it been an inflection point, f double prime would have changed its sign at that point. But it does not, so it is not, so that means if f double prime is not changing sign at x is equal to 0, that just means x is equal to 0 is not an inflection point. In fact, if we get back to figure 9.10, here we have the graph of y is equal to x raised to the power 4, and we see here that x is equal to 0 is surely not an inflection point. In fact, it's a global minimum. It's not an inflection point. At x is equal to 0, the function does not change from being convex to concave or vice versa. In fact, f double prime x is greater than 0 for all x not equal to 0. So here the function is, all throughout, the function is convex. And here, in fact, x is equal to 0 is a global minimum. It is definitely not an inflection point. So now we take up another question. Let's take up another question. Find possible inflection points for this. F of x is equal to the same case we talked about earlier, 1 by 9x cubed minus 1 by 6x squared minus 2 by 3x plus 1. 1 by 9x cubed minus 1 by 6x squared minus 2 by 3x plus 1. Again, we are going to take up the first derivative, which is going to be 1 by 9 multiplied by 3. So it's going to be 1 by 3x squared minus 1 by 6 multiplied by 2. That means it's 1 by 3x minus 2 by 3. That is my first derivative. And now let me get to my second derivative. For that, I can write 2 by 3x minus 1 by 3. And that just means I can write this as 2 by 3 gets out, x minus, I can now write 1 by 2. Because 2 by 3 multiplied by 1 by 2 is 1 by 3. And obviously, if we want to find out the possible inflection points, for that what we do is we first of all set f double prime x equal to 0, and for that we can then write 2 by 3 x minus 1 by 2 is equal to 0. That means x is equal to 1 by 2. But again, as I said, just looking at this does not suffice. we still don't know whether x is equal to 1 by 2 is an inflection point. And to check whether it is indeed an inflection point, we have to look at the fact that f double prime x, it should change sign at x is equal to 1 by 2. So in fact we see that, okay, so this is my f double prime x. I see that f double prime x is in fact less than 0 when x is less than half. If x is less than half, it is less than 0. Also, I know that f double prime 1 by 2 is equal to 0, and also I know that if I look at f double prime x, when x is more than 1 by 2, then f double prime x is greater than 0. When x is more than 1 by 2. So basically, to the left of 1 by 2, the function is concave. To the right of 1 by 2, the function is convex. To the right of 1 by to the left of 1 by 2, I see that the function is concave. To the right of 1 by 2, the function is convex. And that just means that, so clearly we see that at 1 by 2, f double prime x is changing sign. F double prime is changing sign at 1 by 2, and that just means that x is equal to 1 by 2 is an inflection point for f. We can also have a look at the diagram in this case. So here we can see that when we take up x is equal to, so it's 0 here, 1 here, and this is 1 by 2. So when I say x is equal to 1 by 2, it's an inflection point. That just means, so here, okay, I'm not able to, here I see that the function is, when x is less than 1 by 2, f double prime x is less than 0. That means here the function is concave, and here the function is convex. And that just means that this is the inflection point. We don't have the graph of this function with us, but the point to note here is that we are able to prove that x is equal to 1 by 2, as in the second derivative of this function changes sign at x is equal to 1 by 2, and that just means that x is equal to 1 by 2 is an inflection point for this function f. Now we can get to another question, and that question is that we have to find possible inflection points for f of x equal to x squared multiplied by e raised to the power x, and we have to draw its graph. Now, when we want to find out the possible inflection points, the very first thing we do is we calculate the first derivative, which is f prime x, and for that we have to use the product rule. So first function into derivative of the second plus second function into derivative of the first. So this is my 2x e raised to the power x. This is my first derivative. The second derivative is f double prime x, which is equal to, in this case, so again I first take up x squared e raised to the power x. Again I use the product rule, so I get x squared e raised to the power x plus 2x e raised to the power x plus 2. Again here I can write x e raised to the power x plus e raised to the power x, and that just gives me x squared e raised to the power x plus 2x e raised to the power x plus 2x e raised to the power x plus 2e raised to the power x, and that just means I have 2e raised to the power x plus 4x e raised to the power x. Plus x squared e raised to the power x. So that in fact gives us, this can be written as e raised to the power x, and then I can write 2 plus 4x plus x squared, which can then be written as, now I can write f double prime x is equal to e raised to the power x squared plus 4x plus 2. Now it's very simple. I can just write this as e raised to the power x minus x1, x minus x2. Now that will give us, if I just equate this to 0, e raised to the power x just cannot be 0. So we are going to have x is equal to x1 and x is equal to x2. That just means here we are going to solve this quadratic equation, x squared plus 4x plus 2 equal to x squared plus 4x plus 2 equal to 0. If we do that, so I can just do that separately here. I want to solve x squared plus 4x plus 2. For that I can write, it's minus b plus minus under root b squared minus 4ac, so 4 ones are 4, 2s are 8, minus 4ac divided by 2a, so it's just 2. This will give us minus 4 plus minus under root 8 divided by 2, which is equal to minus 4 plus minus, now we can write 2 under root 2 because it's root 4 multiplied by 2. 4 gets out, you just have 2 then divided by 2. This is equal to minus 2 plus minus root 2. So that means you have one root is minus 2 plus root 2, the other is minus 2 minus root 2, and that just means that in this case x1 is equal to minus 2, let's say minus root 2, and x2 is equal to minus 2 plus root 2. And so these are the two roots of that quadratic equation. Which quadratic equation? This quadratic equation. And if we take a look at the sign diagram again, for that we have to be clear about, we have to actually look at, we can think of this product, this term and then this term, and then we can think of their product and have a look at the sign diagram. Now from this I know that the function f has got inflection points at x is equal to x1 and at x is equal to x2, wherein x1 and x2 are these. I can just write f has inflection points no, I should not say that. I should actually be careful about this particular concept. I know that f double prime x is equal to 0 when x1 is this and x2 is this. So from this we just have this necessary condition in this case. So I can't say that f has inflection points at x is equal to x1 and at x is equal to x2. To ascertain this, I have to look at how the sign of f double prime x changes at x1 and at x2. So for that, again we have to take a look at the sign diagram. If by looking at the sign diagram I see that f double prime x changes sign at these 2 points, only then I can be sure of these 2 points being inflection points. How did I get these 2 points? I set f double prime x equal to 0. So f double prime x is equal to 0 at these 2 points. So obviously we have to start with the necessary condition. That is something which is a necessary condition. I mean f double prime c is equal to 0. I know that that is a necessary condition for c to be an inflection point. That is something we have to be very careful about. Now if I look at the sign diagram, it is going to be this. Here we see we have x1, we have deliberately chosen x1 to be minus 2 minus root 2, because if that is the case, and let's put root 2 as 1.414, so minus 2 minus root 2 would be approximately equal to minus 3.41, let's say, and minus 2 plus root 2 would be approximately equal to minus 0.59, and that's why we have chosen x1 and x2 to be written this way, as in, x1 comes, let's say, x1 lies to the left of x2. Think about it that way, so that it's easier to just visualize the number line and get to the sign diagram clearly. And here we know that, okay, here I should write f double prime x. F double prime x is equal to e raised to the power x, x minus x1, x minus x2. So again, we first take a look at e raised to the power x, x minus x1. We can just ignore e raised to the power x and focus on x minus x1. So x minus x1 is greater than 0 when x is greater than x1. So clearly that's the case. It's plus and a minus here. And if I take a look at x minus x2, now let's just take up x minus x2. Again, in this case, that is greater than 0 when x is greater than x2. So that's here. It's minus, and here also I can say that e raised to the power x, x multiplied by x e raised to the power x, x minus x1, or e raised to the power x multiplied by x minus x1. This is less than 0 if x is less than x1, and that's what we have seen. Again, x minus x2 is less than 0 when x is less than x2. So that's what we see here. But if I now take up f double prime x, we have to just take up the product of these two, and here we see that it's a minus minus, the product is again plus. Here it's a plus minus, the product is minus, and here it's plus plus, so the product is plus. So what we see here is that in this case we see that f double prime x goes from positive to negative. If it goes from positive to negative, so if I say that f double prime x is positive, that just means, and here when I say f double prime x is going from positive to negative, that means at x1 the function changes from being convex to being concave. So clearly we see here it is convex and here it is concave. That's how we have seen. Also at x2 we see that the function, that f double prime x, it changes sign at x is equal to x2 also. And here we see, since it goes from negative to positive, again that means the function changes from being concave to being convex, and that's what we see here. It's concave here and convex here, and that's exactly what we see. So that means if I want to find out the possible inflection points, what are the inflection points? x1 and x2, wherein x1 is approximately equal to minus 3.41, x2 is approximately equal to minus 0.59. So here we see that the graph is convex in the interval. I can say here that the graph is okay, I can just write it. I can write that the graph is convex in the interval minus infinity to x1 and it is concave. Okay, no, not that. It is convex in the intervals this and the graph is convex in these intervals minus infinity to x1, x2 till infinity. We can see that in the diagram, minus infinity to x1 and x2 till infinity. We see that the graph is convex in these two intervals. It is concave in the interval x1 to x2. It is concave in the interval x1 to x2. So clearly it's clear here that this is the case, and now I can write the graph is okay. I have made one mistake. I should actually go for this. I'll just let you know why. And it is concave in x1, x2. So why have I put this half open and half open interval here? For that, let's just take a look at the diagram again. So in this case, as I already know that if I want to think of if I want to think of this, obviously here I see that okay, in this case I know that if x is if x is less than x1, in fact I can say that if x is less than equal to x1, that just means f double prime x is since x is less than equal to x1, and okay, so let me write it here. X is less than equal to x1. That means obviously x is less than x2. X is less than x2 in this case, and x is less than equal to x1. So that just means that f double prime x is less than, sorry, not that, if this is less than equal to, so I know that in this case, if x is less than x1, obviously x is going to be less than x2. So if it is a less than x, so it's a minus here and it's a minus here, then it's obviously positive. But if x is equal to x1, then the whole thing becomes 0. So that means I can now write f double prime x greater than equal to 0. And if that is the case, that just means I have to include x1 in this case. And this just implies that the function is convex. And the same story goes if I talk about x2 till infinity. Obviously, in that case also, I know that if x is greater than x2, or let's say x is greater than equal to x2, in that case x minus x2 is greater than equal to 0. Or in other words, I know that if x is equal to x2 or if x is greater than x2, that just means x is greater than x1. So that means this is positive, and this can either be positive or if it is or if it is 0. So both ways, f double prime x is going to be greater than equal to 0. That just means obviously again we will have to consider x2. So here it would be x greater than equal to x2, which I have to consider. Again, f double prime x would be greater than equal to 0. So again, in this case, we are going to take up the fact that the function is, or the graph is, convex in the intervals minus infinity to x1 and x2 till infinity. Also, I know that the graph is concave in x1 to x2. So if x is between x1 and x2, as what we have seen here, again, if x is greater than equal to x1, or if, obviously again let's get to this way, that let's say x is greater than equal to x1. If x is greater than equal to x1 but x is less than equal to x2, it is greater than equal to x1 but it is less than equal to x2. What do we see from the diagram? So in this case, if we are between x1 and x2, obviously we have plus here and f plus here and minus here. That means you have a minus here. That means if you are between x1 and x2, obviously that means f double prime x is less than 0. But if you are at x1 and at x2, that means your f double prime x is equal to 0. So from x1 till x2, both inclusive, f double prime x will be less than equal to 0. And that just means the function is concave in the interval x1 till x2. So now we can have a look at the graph of the function, and for that let's just get to this diagram. So here we have the graph of the function, and in this case you again see that if you take a look at the inflection points, the inflection points are at x1 and x2. and x1 is, as we all know, x1 is approximately equal to minus 3.41, x2 is approximately equal to minus 0.59. And obviously in this case we see that when I say these two are inflection points, that means the function changes changes from being convex to concave or concave to convex at these points. If I talk about minus 3.41, we see that it is somewhere here, and clearly we see that the function changes from being, obviously we know from the diagram, we know from this that the function changes in this case. If I just take a look at minus 3.41, from this I know that the function changes from being convex to concave, and that's exactly what I see here. It changes from being convex to concave. Also, if I take a look at minus 0.59, that would be somewhere around this. So it's minus 0.59, it would be somewhere around this. And obviously here also I see that the function changes from being concave to being convex, and that's exactly what I see here. It changes from being concave to being convex. So clearly from the graph also we have kind of verified our result. Now before I take up the next question, in fact it's not a question, it's just a simple example that we have to consider, which has got important economic applications. So that is the fact that you have a firm that produces a commodity using just one input. So the firm is producing a commodity and the input used is just one. So it's not that labor, capital, land, all these factors of production are being used to produce that commodity. That's not the case. So we are considering a firm that produces a commodity using only one input. And here let x is equal to f of v, and v is that input, let's say, and it's greater than equal to 0. So this is my production function. The function f is the production function. Basically it is the maximum production that you can obtain when you use v units of the input. That's the only input we are going to use. So let's say x is equal to f of v. So x is the maximum production that you can obtain when you use v units of input in the production process. So in that sense, f is called the production function. It gives us the maximum output obtainable from the given inputs. So as I said, f here is what we call a production function. Now it is often assumed that when we talk about the marginal product of that input would be f prime v. That just means that as you increase your input, what is the increase in output? As simple as that. So the marginal product, it is assumed that first marginal product increases up to a certain level of output, and then the marginal product starts to decrease. So we know that this is obviously the case in general, that first marginal product up to a certain level, certain production level, let's say up to a certain production level V naught, the marginal product F prime V increases. After that, F prime V decreases. So if f prime v increases up till v naught, and it decreases after V naught. What does that mean? That means, and obviously I know that V naught is greater than equal to 0. So that just means if we assume that the function I'm concerned about is twice differentiable, and I also know that f prime v, that is the marginal product, it is increasing up to a certain production level, and after that production level it starts to decrease. That just means that f double prime v is greater than equal to 0 in 0 to v naught, and f double prime v is less than equal to 0 in this. Obviously that means f double prime v is going to be equal to 0. And again, what we see here is that f double prime is changing sign at x is equal to, or let's say we can think of it this way, f double prime is changing sign at the output level, at the input level v naught. So first, as in before we reach that production level, so I think I've made this mistake. I'll just get back to this. We have a firm that is producing a commodity using only one input, and we have x is equal to f of v. V I know is greater than equal to 0, and x is equal to f of v. X is the maximum production that you can obtain when you use v units of input. F is what I call my production function. Now it is often assumed that up to a certain production level, or in fact not up to a certain production level, I should say up to a certain level of input used, marginal product will be increasing. After that level of input is reached, and when we have got beyond that level of input, the marginal product starts to decrease. So that just means that till the time you reach v naught is the level of input you reach. Till the time you reach v naught, f prime v increases. That means the marginal product increases. After v naught, the marginal product starts to decrease. In that sense, we can say, so if marginal product increases, f prime v increases before we reach v naught, that just means that f double prime v is greater than equal to 0 in this interval 0 to v naught, wherein 0 is included, v naught is not included. And if I know that after we have got beyond, after we have moved beyond v naught, the marginal product starts to decrease. That means f prime v starts to decrease. That just means that f double prime v is less than equal to 0 in the interval v naught till infinity, v naught not included. So that just means that f double prime v naught is equal to 0. And in fact, when our input level is at v naught, f double prime is in fact changing sign with, or in fact I should say f double prime is changing sign at v naught. And if f double prime is changing sign, we see that before that it is convex, after that it is concave. And that just means that v naught is an inflection point, precisely because f double prime is changing sign at v naught. And when I write f prime v, this I know is the marginal product of that input, because this actually shows what happens to our output as our input rises by, let's say, 1 unit. Approximately, as input rises by, let's say, 1 unit, what is the change in output? That is given by f prime v. So if this is the case, that just means I can now write f double prime is changing sign at v naught, and in fact we see that before v naught f is convex, after v naught f is concave. And that just means that v naught is an inflection point. So that's an important application of inflection point in economics. If you look at the graph of the production function, that looks like this one. You can see f is the production function, v naught is an inflection point. You can clearly see before this f is convex and then it is concave. Clearly we see that f double prime is greater than equal to 0 before v naught. It is f double prime is less than equal to 0 after v naught. So clearly the function is changing from being convex to being concave at v naught, and that means v naught is the inflection point of this production function.